Now let's take a look at something which is not really Bayesian, although the title is empirical Bayes. Empirical Bayes is essentially setting the priors by looking at the data, and this is something which real Bayesians do not like. However, you will see in some situation it is helpful, and in some situation it could be really very, very beneficial. The empirical Bayes is divided to two approaches, parametric approach and non-parametric approach. It was Carl Morris essentially proposed this taxonomy, parametric and non-parametric, in his 1983 JASA paper. And let's start with parametric approach. So you have x's observed, but given the parameter theta I, and the likelihood is fi of xi given theta I. Notice that these are not IID, they are just independent. They are not IID because these functions f for the likelihood could be different, fi, and also the theta i's are different. However, the theta is supposed to be given prior, and these priors for theta I are the same, so thetas are considered to be IID. Now the question is, what happens with marginal? And assume that this common hyperparameter that indexes the priors is common and unknown for a moment. The marginal is, by definition, the integral of the likelihood times prior. If you think about the marginal for all data, x1 up to xn, I put this as the x tilde, that one is the integral of the product of the likelihoods times the product of the priors, and differential is d theta 1, d theta 2, up to d theta n. Well, the product and integral in this case can exchange the place because this is the product that separates the variables, and it is equal to the product of the integrals. And we recognize that this integral under the product is essentially the particular marginal mi for the ith case. So the marginal for all data is product of the marginals for the individual cases, which essentially means that these x's are independent. Distributions of the x1 up to xn splits to the product of individual distributions, and that is definition of independence. This is essentially repeated on the top of the page from the fact that marginal for all data is product of the marginals for the individual data. The x's are marginally independent. That happens if the theta I have the same prior. If in addition, these fi's are the same. So on the previous page, these fi's were different, but if these fi's are the same, then these x's are marginally IID, independently, identically distributed. Also, the posterior distribution for theta I is given as we expect by definition, but notice here that we have this hyperparameter, which is unknown, and that posterior distribution depends upon hyperparameter through the marginal and through the prior. This hyperparameter is unknown, but it could be estimated from the x's, because notice on the top of this page, which distribution, marginal distribution for x, does depend upon this parameter. So it could be done in a traditional way to estimate this parameter xc, a known parameter xc from x's via maximum likelihood estimation. And in this context, this is called ML2 approach, or simply moment matching approach. The best thing would be to take a look at some example. Let's assume that Jeremy took 5 IQ tests and that his scores are 98, 107, 90, 89, 88, and 108. If you get X bar here, this would be 98. So average of these scores would be 98. Now assume that for this data, the Jeremy models his scores as normal with theta I sigma square. So this theta I now is not fixed common theta, but for each test, it will be different theta I. Sigma square, as before, is assumed known, and Jeremy elicited that one to be 80. Now these theta i's for different tests are all having IID distribution, normal with mean mu and tau square variance. We don't know mu, we don't know tau square, but our goal is to estimate thetas. So in this case, the xi's are IID because we have the priors, which are IID, normal with mean mu, and remember, the marginal distribution in the normal conjugate case gets the sum of the variances for the likelihood and the prior. According to what we said, we have IID priors, marginally x's are independent, and the distribution, joint distribution of all these x's is product of individual marginals. So these are individual marginals, MIs, and this is the joint distribution. So what would be maximum likelihood estimator? In this case, it is normal distribution, and for mu, in the previous case, we have mu, and we have this parameter here, sigma squared plus tau squared. For mu, the estimator is x bar, and for the tau squared, you really take the difference between s squared minus sigma squared. Sigma squared is known, but s squared, in this case, is the sample variance of x's. Well, this comes from the fact that this tau square has to be positive because it is estimator of the variance. S square is the standard deviation variance of the x's, and sigma square is the variance from the likelihood elicited one. So tau is the difference of those. Of course, the difference, it has to be maximum between 0 and the difference. So these are two estimators, maximum likelihood estimators of the parameters. And with these estimators, we now find the posterior. The posterior for particular theta I, given xi, and given these estimators, is simply the posterior for the conjugate family. But here we plugged in x bar for mu and s squared minus sigma squared for tau squared. So in this case, this B weight in which we take the weighted average between observation xi and mu hat is depending on estimator of tau squared. So for Jeremy's data, S squared is 101. This is sort of a sample variance of all x's, of all scores. And with this one, the B hat is estimated or calculated to be 80 divided by 101. This difference is S squared minus sigma squared, and it is positive. So simply this is the B hat. If this was negative, then the B hat would be 1. Now what happens next? We find the Bayes rule, Bayes estimator, and for this theta 1, we take the weighted average, so this is 20, between 98, which is x bar, and 98, that was observation. For theta 2, we have the weighted average between 89, which is x bar, and 107, which is observation. So this is 20. So we get the estimators of theta for each case. Why it is different than the, for example, taking each case separately? Because this is borrowing strength from all data. So to estimate theta 1, we use the observation x1, but we use also the x bar from all observations, and the weights themselves are depending on all observations. This example is having n Poisson observations with parameter lambda I. They are independent, but parameter lambda I is having prior, which is exponential with parameter mu, hyperparameter mu. Mu in this case is the rate parameter. And we need to find empirical Bayes estimators of all these lambda i's. Notice that for all these n experiments, for all these n observation xi, all lambda i's are different, and we would like to find the lambda I for each. The Bayes estimator for Poisson and exponential, this is the conjugate case, Poisson gamma, exponential is special case of gamma. The posterior distribution is gamma, and the parameters are xi plus 1. This is actually gamma with 1 and mu parameters. So the posterior is gamma, xi plus 1, and other parameter is 1 plus mu. So the expected value for lambda a posteriori is xi plus 1 divided by 1 plus mu. However, this mu is hyperparameter, and it may not be known. So we are going to do this by empirical Bayes. We are going to take a look at the data and specify mu from the data, and then just continue our inference in traditional Bayesian fashion. So the marginal in this case is usual likelihood times prior with respect to integration with respect to lambda I, and this integral can be simplified. So what I am doing here is getting together these exponents and getting e to the minus 1 plus mu times lambda I. Then I notice that the rate parameter here is 1 plus mu. So my rate parameter would be here. I need to divide everything with this expression because I put it in here artificially. I had the lambda to the xi coming here. And x factorial is essentially already gamma, by definition, gamma of xi plus 1. So after small clears, we get the integral of a density. And this is gamma density, and that is 1. And end up with something which is geometric distribution. So m of xi is 1 divided by 1 plus mu raised to the xi. Then mu plus over 1 plus mu is another factor. And we recognize here geometric distribution. Let's review what geometric distribution was. Geometric distribution is essentially the number of experiments until first success, or in one interpretation, or the number of failures until first success. In this case, it is a number of failures until first success. So one fails with probability 1 minus p, and then have success with probability p, and number of failures in independent subsequent trials is 1 minus p raised to the xi, and then after xi failures, there is success. And that could be 0, 1, xi could be 0, 1, 2, and so on and so forth. So that generates a geometric distribution. The parameter p, you can recognize in this case, is equal to mu over 1 plus mu. In usual fashion, we get the marginal to be a product of individual marginals, and product of individual marginals becomes this expression in which you have summation of xi's and p to the n. And then we estimate, by using maximum likelihood approach, the p. In traditional way, we find the logarithm of the likelihood, then take derivative of the logarithm, and set this derivative to be equal to 0. By solving this equation, we find the MLE of p, and that MLE is n divided by n plus summation of xi. If we divide by n numerator and denominator, we end up with p hat estimated as 1 over 1 plus x bar. So mu divided by 1 plus mu is estimated from the data by 1 over 1 plus x bar. This leads to the mu hat estimated as reciprocal of x bar. Now what we did is the following. We got a formally Bayes rule, we got formally a posterior distribution, everything a posteriori depending upon parameter mu. Then we looked at the data via marginal, and we estimated this parameter mu from the data as 1 over x bar. To finish the example, we have this Bayes rule that we found for lambda I. In empirical Bayes, you simply replace mu by mu hat that you estimated from the data, and the lambda I is estimated as xi plus 1 multiplied by this coefficient that involves all data. Notice that there is a borrowing strand, that is lambda i's are estimated by individual observation xi, but also this x bar over 1 minus x bar comes from the whole experiment, from all n observations.